I now call to order the Society's 2508th meeting in what is now the 153rd year since its founding on March 13th, 1871. Good evening, everyone.
Good evening, Larry.
My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's meeting and the lecture by Scott Wolk. The Society is grateful to PSW full-year series sponsors, PSW member Mike Helton and Helton Associates. Thank you, Mike. And to series sponsor, PSW member Joe Schulman. Thank you, Joe. And to the sponsor of tonight's lecture, AC Charania, who unfortunately can't be here tonight. But thank you, AC. We're very fortunate to have been given a donor match gift by a generous supporter who wishes to remain unnamed. It's a 2-for-1 matching gift, so every dollar you give gets us $3. We are coming to the end of this period, which will be January 31st, the last day for the 2-for-1 match. So I implore you all to pony up and make your donations now so that we can make full use of this gift, which, if we get $10,000 in donations that qualify, will bring the Society $30,000, which will cover a good portion of our expenses. Some of you may not know, but this room is not free. And the refreshments we have afterwards are also not free. And doing the videos is not free. In fact, very few things in life are free. But the labor that goes into all of this is donated. We have no paid staff. So please be generous and help us meet this 2-for-1 match and continue to pay the $2,000 it costs for every lecture to rent this room. Now, with that bad news, we'll move on. I'm pleased to announce the following new members. Lauren Benson, an AI research scientist with Leidos, interested in mathematics, complex networks, artificial neural networks, machine learning, with a recent focus on space systems, who learned at PSW from, well, we're not sure where, but her interest in becoming a member is from attending a number of lectures. Richard Henry, a professor of physics and astronomy at Johns Hopkins University, who is a returning member after a long hiatus, who is interested in quantum mechanics, and who says he learned of PSW a long time ago, but does not tell us how. And finally, tonight's speaker, Scott Wolk, who learned of PSW, I believe, from our invitation to him to speak here tonight, and whose interests will be clear in part, at least, from tonight's lecture. But I don't think he's going to talk about his great interest in playing ice hockey. We welcome them to membership. All members are entitled to a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington. And if you've not received yours, please come see me after the meeting. And if you're interested in membership, you can access a membership application on the PSW website. On the home page, you just click on the blue Join button at the upper right-hand corner and follow the prompts. The only real requirement for becoming a member is a genuine interest in science and paying dues. Finally, if you become a member, you are entitled to purchase a ribbon of the Society and wear it whenever you please. The ribbon, as I'll tell you later, is got a lot of symbolism in it and evokes our founder, Joseph Henry, who studied induction and for whom the unit of inductance, the Henry, is named. Recording Secretary Scott Matthews will now present the minutes of the 2507th meeting and the lecture by Javier Garay on the engineering challenges of fusion energy production. Scott.
Thank you, Larry. On January 12th, 2025, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room of the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2507th meeting of the Society to order at 8:02 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Joanne Hewitt titled, "The Science Driving Particle Physics and Big Accelerators." The minutes were approved as read. President Milstein then introduced the speaker for the evening, Javier Garay of the University of California at San Diego. His lecture was titled, "Fusion Energy Meeting the Engineering Challenges." The speaker began by presenting the possible advantages of fusion energy, saying that it was clean, safe, dispatchable, meaning always available, and used an abundant source of fuel. He discussed the increased demand for electric power driven by economic growth, electric vehicles, and the emergence of artificial intelligence. He presented a graphical representation of DT fusion, the fusion of deuterium and tritium, to form an alpha particle and a neutron. He showed a picture of an oil tanker, which, when fully loaded, displaced 900,000 tons of seawater. He claimed that this quantity of seawater contained about 40 liters of deuterium, which, when fused with tritium, would produce more energy than the oil in the tanker. Garay then presented the two primary confinement schemes currently being used in fusion research: inertial confinement and magnetic confinement. As examples of operational facilities, he showed pictures of the National Ignition Facility, or NIF, at Lawrence Livermore, and the D3D National Fusion Facility at UC San Diego. As examples of facilities currently under development, he showed images from several private companies, including Pacific Fusion, Exemer Energy, Tokamak Energy, and Commonwealth Fusion Systems. The speaker mentioned two recent technological advancements, which he called breakthroughs: the demonstration of fusion ignition at the NIF and the development of superconducting magnetic confinement. He showed images of the NIF, including the building housing the 192 lasers, the target chamber, the hull room, and the fuel pellet. He then showed images of superconducting coils produced in the SPARC project, capable of generating 20 Tesla magnetic fields. Garay then presented an overview of the ARES program, Advanced Research Innovation and Evaluation Study, at UC San Diego. This program included contributions from several universities, government labs, and private industry. He discussed other research programs created or organized by UC San Diego, including the 2024 Fusion Energy Workshop and the Fusion Energy Institute. The speaker presented three engineering challenges associated with fusion research. The first was material synthesis and characterization. He showed a list of requirements for plasma-facing components, which included low erosion rate, low vapor pressure, low retention of hydrogen isotopes, low activation by neutrons, and low surface morphology changes. He showed micrographs of tungsten as a function of radiation dose, demonstrating the changes in microstructure that occur due to the creation of defects, precipitates, and voids. Garay discussed some of the mechanisms by which these radiation-induced changes occur, including atomic diffusion, vacancy formation, interstitial migration, and the creation and movement of dislocations. He specifically discussed the changes in thermal conductivity due to changes in microstructure. The second engineering challenge was fuel capsule target design. He showed diagrams of the fuel capsules currently being used in inertial confinement research, including the cryogenic DT fuel, nanostructured inner material, the outer shell, and the hull room. Garay discussed the time evolution of the pressure wave generated by laser irradiation and how that pressure profile was influenced by the properties of the fuel capsule. The speaker showed examples of 3D printed nanomaterials used to study the implosion of targets. The third engineering challenge was tritium breeding and cooling. Gray said that tritium does not occur naturally in any significant quantities, and that as a result, all tritium fuel has to be created through breeding. He described the technique of surrounding a fusion plasma with a lithium-containing breeder blanket, such that the lithium can absorb neutrons to produce tritium and alpha particles. The tritium can be extracted for use as fuel, and the alpha particles can be used to transfer energy to a thermal absorber. Gray discussed the use of heat transfer fluids to move the thermal energy from the reactor and breeder blanket to the electric power generation system. He briefly described molten metal circulation systems, where the liquid metal acts both as a tritium breeder and a heat transfer fluid. Garay ended his talk by thanking collaborators and acknowledging funding sources. The lecture was followed by a question and answer session. A member asked the speaker to speculate about when we would have practical solutions to all the engineering problems discussed in the talk. Garay responded that it depended on the resources. He said that with more investment, many problems could be solved in parallel, greatly increasing the rate of progress. A member asked about other hydrogen fusion reactions, specifically helium-3 reactions. The speaker responded that DT reactions have the highest cross-section and can therefore occur at temperatures and pressures that have been achieved in the laboratory. A member asked about the possibility of a, quote, nightmare scenario where no materials could ever meet the requirements of fusion-based power generation systems. Garay said that although this was possible, he believed that we have yet to exhaust the materials currently available and that new materials are continuously being developed. A viewer on the live stream commented that we cannot burn carbon in space and asked if this form of energy production could be utilized in spacecraft. Garay responded, yes. A member asked about combining fusion reactors with molten salt reactors, indicating that molten salt reactors could provide the tritium for the fusion reactor, while the fusion reactor provides neutrons for the molten salt reactor. The speaker responded that people are considering hybrid reactors that would combine fission and fusion in the same reactor. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 1 of the PSW Bulletin. He then announced speakers of upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,507th meeting of the Society at 9:52 p.m. Eastern Time. Temperature in Washington, D.C., 0.5 Celsius. Weather, cloudy. Audience in the Powell Auditorium, 69. Viewers on the live stream, 52, for a total of 121 live viewers. Views of the video in the first 2 weeks, 426. Respectfully submitted, Scott Matthews, Recording Secretary.
Hearing no comments on the minutes, I will entertain a motion to accept the minutes subject to those corrections and any that come in through the web. I do have several motions. Do I have any seconds? And all members in favor? All members opposed? The minutes are therefore accepted with subject to those corrections and will be posted to the website in due course. Thankfully, we now turn to tonight's lecture by Scott Wolk on highlights of the X-ray universe, Chandra's first 25 years of observations, and more to come. Scott is senior astrophysicist at the Harvard-Smithsonian Astrophysical Observatory, one of Chandra's flight directors, and a member of the AXIS team, that's the Advanced X-ray Imaging Satellite, recently selected for NASA Phase A study. Previously, Scott held a variety of positions on the Chandra team and served as a principal investigator, co-investigator, or a team member on a number of Explorer programs. He started graduate school studying to be a planetary scientist. But because basically there weren't very many planetary missions at the time, he turned to X-ray astronomy. And he started with Chandra immediately after graduate school as an operations scientist. And he's remained with the team ever since. But fate has been kind. And recently he's been able to come full circle back to studying planets. Only he's not studying nearby planets, he's studying exoplanets using the unique capabilities of Chandra. Among notable research, first, Scott and PSW member Carrie Liss discovered charge exchange in comets elsewhere in the solar system and beyond. And Scott and colleagues pioneered the study of exoplanets in the X-ray regime, measuring the first transit of an exoplanet at high energy. Most recently, he's been involved in a series of observations of protostars with the James Webb Space Telescope. He's an author on more than 160 technical papers on a wide range of subjects. Among other honors and awards, he has served on several NASA panels, including a NASA Study Analysis Group, Great Observatories, the NASA New Great Observatories, SAG, and the NASA New Athena Science Team. Scott earned an AB at Cornell University and a PhD in astrophysics at the State University of New York at Stony Brook. All questions will be fielded after the lecture during the Q&A session. Scott, the stage is yours.
Thank you, Larry, and thank you for that warm welcome. And thanks to Kerry, if he's here yet, for the invitation. It's very overwhelming to be here to speak before you, listening to the speaker before me, and the subject matter that's being discussed. I'm overwhelmed. But I'm also really happy to be here to share with you a little bit of an adventure that I've been on for the last 25 years, more or less, with the Chandra X-ray Observatory. Was asked to put that picture that you're looking at to scale, and I'm going to ask one question before we get too far into this. Is there any way to kill the lights that are right on top of the screen? Some of the images I'm going to show later on are a lot of fun. Okay. But I was asked to give a concept of what you're looking at there. The Chandra X-ray Telescope basically is the size of the open space in this room. You can imagine the solar panels filling the space in front of us, and then the spacecraft going back there just about to where that cocktail table is relative to the screen. So that's the size of the observatory we're talking about. It's not particularly large, but it is particularly heavy. So we're observing X-rays, and we're observing them from space. And the reason we do that is a very good one. X-rays don't penetrate the atmosphere. And when I say it's a very good thing, I mean it's a very good thing. Because if the X-rays penetrated the atmosphere, that would not be good for, as we say, multicellular life, which is most of us in the audience. So when we're looking at, I apologize. The first time I do this and I get it wrong. So the reason that we're looking at the X-ray or in the gamma ray or in the infrared, these wavelengths do not make it to the ground. They have to be observed in space. And the original great observatories, we had the Compton Gamma-ray Observatory, the Chandra X-ray Observatory, Hubble, and the Spitzer Space Telescope. And now Spitzer has been superseded with the Webb Telescope. And I'm very proud of my ability to overlay Webb right in the correct spot on this plot. There's also radio waves do make it to the ground. The electromagnetic spectrum is very wide, and most physics don't care about it. They occur at multiple wavelengths. And to understand what's going on, we look at multiple wavelengths. That's how we understand the universe, and that's the power of the Great Observatories program that was put forth in the 80s and then deployed in the 80s, 90s, and early in this millennium. I'm going to start our story roughly with the beginning of X-ray astronomy and with a member of the Cosmos Club, Riccardo Giacconi, who was also the head of our department before I arrived and also ran Space Telescope after that. This is the first X-ray detector. It's about the size of this lectern, and I have to say it is a challenge not to use this. So let's put that back down. So it had a Geiger counter, two Geiger counters that would measure X-rays at independent frequencies, scintillators on top that were sensitive to electrons, so you could reject electrons versus what were X-rays. And this was launched in a suborbital payload with the idea of looking at the moon. At this point, we knew that the sun was an X-ray source. The next obvious thing to look at would be the moon, and to look at if the moon was fluorescing X-rays back to us. The mission was about 350 seconds. It was a suborbital flight that made it up to about 280 kilometers. This instrument rotated at about 2 rotations a second. So it did a total of about 180 scans across the sky like this, going across the moon and everything else. The result was published fairly quickly by modern standards, about 5 months, 6 months later. The result was this scan across the sky. There's a little kick up here where the moon is, but overall there's just this huge, big peak, roughly in the direction of Scorpius. So the first bright X-ray source in Scorpius, what to call it? Scorpius X1. Because we're like that and very uncreative, and so that's the name. SCO-X1 stuck. In a few years, it was understood to be an accreting binary system. The other result in this study was that the background isn't actually zero. The background's actually, especially in the softer as a spectrum, it's soft, and it's fairly high. So in 1962, we now knew of one X-ray source outside of our solar system and 2 within the solar system. Therefore, it was determined that we must build an orbiting X-ray observatory. And this is a proposal sent unsolicited to NASA in 1963. And it is for a telescope that has a diameter of about 4 feet and runs from about this monitor here to the coffee table back there, and has a focus of about 1 arc second. Now, the suggestion wasn't to build this immediately. It was to build a couple of intervening spacecraft. But this was proposed formally to NASA, again unsolicited, in 1976 by Ricardo Giacconi and Harvey Tannenbaum. And that was submitted to the 1980 decadal, which concluded that what was called at that point the Advanced X-ray Astrophysics Facility will profoundly influence and enhance the development of nearly all areas of astronomy. And that became Chandra. And I put it this way because it is almost the exact prescription and design that was put forth by Ricardo a year after the first X-ray source was detected outside of the solar system. Let's see how we do here. So X-ray telescopes have to be done differently. X-rays are wonderful for X-rays. They penetrate your skin, they can penetrate your bone, they penetrate right through mirrors. So you can't use what we call normal incidence optics to focus X-rays. Instead, we skip stones. So a normal telescope like Hubble or like Webb is made with a mirror that is a conic section that focuses light in front of it, and then eventually we deflect things backward. We'll normally deflect things backward through a tube like this. X-ray telescopes can't work that way. What we end up doing is we end up skipping the X-rays ever so gently at about a 1 degree, we call it a graze angle, to a focus in the distance. And so if you're thinking of an X-ray looking at that optic, the optic might be 4 feet across, but you're just skipping off little bits of it. So even though the Chandra mirror, I said, is 4 feet in diameter, so it's about that big in diameter, the overall effective area that X-rays can see is almost exactly the size of this shield in front of me. It's about 1,000 square centimeters, a little bit less. But because of the fact that you have to have this long conical surface. You have this very large area that has to be polished. So the polished area of the Chandra mirrors is actually equivalent to a 5-meter telescope. So there's more polishing to be done here than was done on the Hubble Space Telescope, and the precision has to be a little bit higher because our wavelength is so small. We're looking at wavelengths as small as 1.5 angstroms. So that's the polishing limit and the smoothness limit we have to have on this telescope. So it's really an incredible technological accomplishment, and then you have to align these optics almost perfectly, because any error in this alignment is going to be amplified as the light goes down the 10-foot long beam. So this is finally what we ended up with Chandra. It looks a lot like the picture in terms of the solar panels. It works a little bit like a refracting telescope. The optics are in front, and we send light to the back. And there are 2 instruments in the back. There's a microchannel plate that we call the high-resolution camera. It is very high resolution, but it's basically a black and white camera. It doesn't have a lot of energy sensitivity. Then there's an ASIS camera. That's a CCD camera. It's a little more complicated than what's in your phones, but it's the same kind of idea. It has energy sensitivity in addition to the imaging ability. And it is about the energy resolution of your eye, depending on how good your particular eyes are. My wife says I should be seen for color blindness, but the overall effect is that it can discern some colors, but it doesn't really know things perfectly. So both of these instruments have an imaging array and a spectroscopy array. And so the spectroscopy array is aligned for, well, gratings. And in front of each, or at the back end of each of the optics, we have little facets that are about the size of a quarter attached next to each other, and they simply act as transmission gratings to spread the light over those detectors. I also want to point out the real power of Chandra comes from its spatial resolution. So the spatial resolution of Chandra is about the same as the Hubble Space Telescope. It's about half of an arcsecond. And what that means is we can focus all the light from a point source onto a single pixel. And then also, because we're at very high altitude over the Earth, and I'll explain that in a moment, we have almost no background. We can stare at a target in space for 1 million seconds, which is about 10 days, and we will collect 2 background detections in each pixel. So if over the course of 10 days we see 10 X-rays, that's a 5 sigma detection. 10 X-rays. And we do sometimes name them. All right. So those are our gratings. So this is where we need the sound.
10, 9,
Yep.
8, 7, 6, 5, 4, 3. We have a go for engine start. 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
Houston Columbia is in the roll. We've got a fuel cell PH number 1.
Roger roll, Columbia, we're looking at.
So we were the heaviest payload ever delivered by the shuttle mission program. Our launch on Columbia in 1999 was the first mission commanded by a female, Eileen Collins.
Columbia, Houston, we'd like AC bus sensors off. We're evaluating the fuel cell.
And the call you just heard was one of many concerns in the flight. We ended up a couple of kilometers short. There's actually a very long, this was a 7 minutes to orbit, but I think the YouTube video that covers everything that happened in those 7 minutes is about 20 minutes long. But everything at the end of the day went well, and we made it into space.
And Houston, what you're seeing is the actual moment of deploy there when we take the switch to deploy, and it's so quiet. We were just amazed, but you look out and this thing is so big, you certainly know that it's moving towards you and over the head of the shuttle.
Okay, that's the voice of Katie Coleman, the mission specialist who deployed Chandra.
You're getting a little bit better view of Chandra out in front of the IUS there. And I know that a lot of people have seen Chandra as it's been constructed and seen it as it's been installed in the shuttle, but I will tell you there is nothing as beautiful as Chandra sailing off on its way to work.
It was released almost as soon as the shuttle reached orbit because on the back of Chandra was a rocket, the inertial upper stage, and it isn't clear how comfortable the astronauts were to have a rocket pointed directly at them while they were in the shuttle bay. I'm going to push off to our baby pictures. So these are my baby pictures of Chandra, or at least 3 of my favorites. This is the launch. This is Chandra in the shuttle bay. This is some of the last images seen of Chandra. The inertial upper stage rocket is here, and then this is Chandra itself at the other end, and it's going to get pushed so the shuttle puts it into low Earth orbit, and then we are boosted by 2 bursts from that inertial upper stage, and then eventually 5 burns of our onboard rockets to get us into a peculiar orbit that comes fairly close to the Earth at perigee, and at apogee goes about 1/3 of the way to the moon. And the reason for this peculiar orbit has very much to do with this city, because the Hubble Space Telescope was launched, and a big selling point was that it was serviceable, which meant you can go up there and you could change out pieces, and all it required was Congress funding those pieces. And then they realized how expensive that was. So we got orders to, whatever you do, you cannot be serviceable. So this orbit was chosen and has had some very wonderful side effects that we hadn't actually thought about. The most important was that it allows us to look at things for much longer than we were used to. In low Earth orbit, you generally look at things for about 45 minutes at a time, and then the Earth gets in the way. And you come back 45 minutes later, and then the Earth gets in the way. This is very hard on efficiency, and it's very hard when the subject that you're looking at is changing. Chandra, on the other hand, I'm going to show you a particular observation that we took, which was basically 10 solid days. 80% efficiency of the mission. We literally just spent all of our time, except when we were behind the Earth, looking at this thing. And it's just, still to this day, we are getting these kinds of efficiency levels because we don't have to take a break whenever we go behind the Earth. One other wonderful feature of Chandra is it's intrinsically a timing mission. We read out our detectors every few seconds, or in some cases, milliseconds or microseconds. And it means that every time an X-ray strikes the spacecraft, we know what happened to within a couple of seconds. And then with the gratings in the way, we have not only the low energy resolution color, but we also have high energy resolution color. And I love this image because this target right here, the supernova remnant's about 1 minute across, but then we disperse the light, and you can see there are soft X-rays, medium X-rays, and hard X-rays, just like your eye does. That color scheme is basically representative of the energy that ACIS sees, that color detector. But then because of the spectroscopy, we know the exact energies of this is oxygen with only 1 electron. This is oxygen with no electrons. This is neon with only 1 electron, neon with no electrons. Incredibly highly excited gases that all compose this particular supernova remnant. Okay, so I gave you a little hint. What are sources of X-rays? Supernova remnants is a thing, but this is really a physics experiment. And there's 4 kinds of physics that give rise to X-ray signals predominantly, really predominantly 3. Shock waves, ionized gas, when energy is produced and driven into a system of atoms very quickly, they heat up, they lose their electrons, and eventually they give rise to X-rays. Magnetic field, synchrotron emission is when you have a strong magnetic field, and then you send electrons down that line and they spin, and that produces energy, and that produces X-rays. So when we're seeing the synchrotron radiation, we're seeing this magnetic field represented in terms of X-rays that we can see. And then gravity, accretion. when you have matter falling from a great distance, and this is a cluster of galaxies I'm showing here. So the distances here are millions of light years that particles are falling from here to there and screaming on their way down, giving rise to these X-rays. So that's scientifically how the X-rays are formed. What emits X-rays in the sky? I think that covers it. That's pretty much everything. That's everything from planets to stars to supernovae, black holes, galaxies, one galaxy, lots of galaxies, galaxies flying around. So for the next phase of this talk, just to give some context, I'm going to refer back to something called the Pathways of Discovery. This is the Astronomy Decadal Survey. As one might guess, the National Science Foundation instructs or helps astronomers fund a study once a decade to sort of lay out the goals for the next 10 years. In fact, I referenced the one from 1980, which found that Chandra would do a lot of wonderful things. In 1990, it was said that Chandra is the next thing we should do. In 2000, it was James Webb is the next thing we should do. In 2010, it was the Roman Space Observatory is the next thing we should do. And what this decadal said, this Pathways to Discovery, they identified 3 very specific pathways. They talked about worlds and suns in context. They talked about investigating the nature of extreme cosmic physics, and then cosmic ecosystems. So the interesting thing here is that while Chandra was written up there in 1963 saying we should do this, and it was proposed in 1980 that here's how we're going to do this, we're standing here now almost over 60 years later, and it is still relevant. It is still doing the things that astronomers think are most important to be done. And what I'm going to do now is I'm going to take those pillars, and I'm going to talk to sort of some of the different things that Chandra has done. And I'm going to work from the outside in. I'm going to do this for a very specific reason. As Larry said, I came into this as a planetary scientist, became a stellar astronomer. This is not my field. So this is very dangerous territory for me, talking about this. And so I organized this talk to start with the stuff I don't know, to end with the stuff I know, with the hope being that if you come up with questions about this, you'll forget it in an hour. So with that warning, I want to talk about dark matter. And what you're looking at here is a Hubble image of a couple of clusters of galaxies. You might be able to notice there's galaxies over here, and there's some galaxies over here. There's some space in between them. So those galaxies are a few billion light years away, but there's other galaxies behind those. And so the light from the galaxies behind those is bent by gravitational lensing. You can take a look at how much bending occurs based on how far things are from the center, and you can measure the mass in these 2 clusters of galaxies. So, I don't know, there's a few hundred galaxies in each of these clusters, and with this Hubble data, you can measure where all the mass is, and that mass is there. That gravity is affecting things. We know the mass is there. Then you can go with Chandra and you can find out where the matter is that is what we call normal matter, the things that you and I are made out of, the things that you can interact with. That's what Chandra is sensitive to in its X-ray images. And that's where the normal matter is. You see this peculiar shape. It's called the bullet cluster because of this shape. And what has happened is the galaxy on the left used to be the galaxy on the right, and the galaxy or a cluster of galaxies on the left used to be the cluster of galaxies on the right, and vice versa. These 2 clusters of hundreds of galaxies have flown through each other. And the normal matter has been interrupted by this. it's been heated by this, and this is what we see. So this is the results of that car accident. But the mass is still here. So what you're seeing here is dark matter. Dark matter is staying with the galaxies and not interacting, even though the clusters of galaxies have gone through each other. The stars may have gone left or right, but something just went right on through. So what this stuff isn't exactly clear. It's called weakly interacting massive particles because it didn't interact much, but it's got to have weight. It could be something called axions, which are equally poorly described, or it could just be that every single one of these clusters has a black hole in the middle of it that we can't quite see because black holes don't emit anything. But this is proof in this image that most of the matter in these galaxies is not what we call normal matter. And this is just a little simulation of that collision put together at the CFA. And you can see that the normal matter and the dark matter start together. But as they interact, the dark matter just kind of ignores the collision. But the normal matter experiences the collision and heats up. Okay, that's dark matter. Let's move over to dark energy. So this is another image of a different cluster of galaxies. This one's called Abell 85, and what you see is the same kind of effect. The normal matter has become heated by gravitational infall, and so this is just a distribution of the normal matter of this particular galaxy. In this other image, this is an illustrious simulation of the structure of the universe. So it starts with a little bit of structure out here, and as we move forward in time, it becomes more and more structured. And I was talking to somebody at the cocktail hour before this about this, but this is sort of what the universe looks like now. There are these clusters of galaxies and relationships between the clusters of galaxies, and then giant voids in space. That's what we see right now. So one of the scientists at the CFA, Alexei Vaklinin, took a look at all of these clusters of galaxies that are near to the Earth. So this is the mass and the number of galaxies nearby the Earth. And so there's lots of small clusters of galaxies, not a lot of large clusters of galaxies. And this is a model of the universe which says that there's about the amount of matter that was estimated in the previous image, 1/4 the closure density of the universe, and that's about it. And it fits perfectly to the local galaxies. Galaxy clusters. Remember, each of these is hundreds of galaxies. But when you move to, now if there's no dark energy, as you move further and further away, there's a prediction from that model I showed you that this should be the distribution in prior time. So there's a few less big ones, a few less small ones, but overall the same basic shape. And you can see the first couple detections here seem to follow that trend. But as we developed more data and found more clusters at high Z, we deviated from that trend. And the conclusion from this plot right here is that a universe at 1/4 of the closure density and no dark energy is inconsistent with the data as observed by Chandra. However, if you assume a dark energy constant of about 0.75, everything lines up again. So this is the conclusion from the Chandra observations of clusters, and these have been expanded to further and further away, but this still holds. The Chandra data argue for about an about amount of matter in the universe, both dark and normal, of about 0.25, and the remainder of the closure energy of the universe being in this dark energy. That can be combined with other observations that are completely independent, observations which have to do with what they call type 1a supernova, which we think are a standard candle, or with the changes when you look at the cosmic microwave background and the frequency of variations you see there. Those three observations are completely independent of each other, yet they all intersect in their plots in terms of what they think that the lambda number must be, about 0.75, and what they believe in this case the total mass or total closure density of the universe must be, which is about 1. And this is about where we are today. What we on our team like to point out is that while the 4 models all basically have this little spot in them where they all agree to 3 sigma, the galaxy cluster measurements that I talked about are unique in their ability to basically confine both dimensions of this problem on their own. So roughly, that is the what's in the universe as far as Chandra has been able to figure out. Now, please forget I told you any of that. We're going to move to the next theme, which is extreme events. And one of the extreme things in the universe is that black hole I mentioned that's in the center of all galaxies, supermassive black hole. So what I'm showing you here is one of my favorite images. This is the galactic center, as imaged by Chandra. What you're seeing is, well, there's the galactic plane. There's loads of gas going up, globes of gas going down. All the little dots you're seeing here are are stars, young stars that are very bright and energetic in X-rays. The black hole at the center of the galaxy is about 10 to the 6 solar masses, and it is what we call starving. There is just no accretion going on in our central black hole right now. What we've done here is I've zoomed in. This is about 3 million total second integration time. So this is about a month's worth of data. And while there are some little peaks here and there, and there's a little event here, those flares that's about 8-9 hours of data. Those are little hiccups. Those are sort of factor of 10 in brightening. More often is what we see here, which the first author referred to as, it's just boring. It's just this black hole at the center of our galaxy sits there and spins a little, but doesn't do a lot. But clearly in the past it did. These events indicate that there were large flares previously. When you look at the center of the galaxy, you see this. That is not the center of our galaxy. That's a magnetar that happens to be nearby. And then occasionally you'll see something flared next to it. That's the center of our galaxy. So the black hole at the center of our galaxy flares a little bit, but there's also some bright stuff right nearby. And I love this image because this is something only Chandra can do, because you need the 1 arc-second resolution of Chandra to tell if you're looking at the black hole at the center of our galaxy or the magnetar that just happens to be nearby. So this is a whole field of science and trying to understand what's going on in the center of our galaxy, which is really, really hard to tease apart if you don't have this kind of splendid spatial resolution. This is just a figure that was given to me to drive home the point. This is called the fundamental plane. This is the radio emission versus the X-ray emission as a function of mass. And sort of all the black holes we know of that are at the center of galaxies, they all live here. So if you look at them in the X-ray, you know what they look like in the radio and vice versa, except for the black hole at the center of our galaxy, which is a huge outlier in terms of quiescence. So we don't know if we live in unique times and if that's important or if all galaxies go through these periods. But at the moment, our galaxy is relatively unusual and relatively quiet. On the other hand, this is an event called Gravity Wave 170717, which means it occurred on August 17th, 2017, which was a Thursday. And I know it was a Thursday because I was coming back from one of our buildings to another one of our buildings, and we got this alert that a gravity wave had gone off, and they knew where it was. So I stopped off at our mission planning office, and I said, we're doing this. Now, I'm not the director. I don't get to make that call, but we're doing this. And so we got on the target within 2 days, and what we saw was this. Can everyone see that X-ray source? Good. There wasn't one. Now, 9 days later, it was there. So when things are changing in space, it's not always a function of getting there quickly. It's getting there at the right time. What we think happened here, so what happened here was two neutron stars collided. And the reason we call it striking gold is we detected gold. And this is fundamental because people didn't know how gold was created naturally until this measurement. So that's just a little nicety. There are supernovae and there are ways that we thought gold was going to be formed, but basically the pathways were tricky. But neutron-neutron star collisions should be able to do it, was what my professor taught me in I can't go back that far, 90. And he was right. Smart guy. This image isn't about the gold so much as about how, when we looked the first time, the jet that was formed by the neutron star collision hadn't quite gotten wide enough for us to see it. And either the beam widened or it hit something in the way and that deflected X-rays into our view. So what we ended up with is now we've been following this for 8 years, 7.5 years, and we can still track this object. As you can see, it got brighter in time, then it got fainter in time, and it follows this law that was expected for a jet afterglow until you get here, about 3 years, 4 years, 5 years later. Now it's deviating. We're not exactly sure, I should say Daryl's not exactly sure, this ain't we, why this is happening. One of the thoughts is that there might be, that this material here that was struck, this material that was struck, that may be having secondary reactions and new materials being made there that is still going through its cooling phase. So there's still a lot to be learned here. This is another one of my favorite images. For those of us who remember the Cosmos series, this is a page from Tycho Brahe's notebook in 1572. He's observing the constellation Cassiopeia, and he's accounting for the stars, A, B, C, D, E, F, G, H, and I. And the reference here for I says Nova Stella. Suddenly, in 1572, a new star showed up, and it stayed there for 2 years. And he recorded the position very well. Tycho Brahe was famous for recording these positions with incredible accuracy. So as telescopes were developed, people went and looked, and this is what they saw. Does everyone see the supernova remnant? No? Anybody? Okay, let me help you. Let me show you the same thing in X-rays. Okay, so what we're looking at here is a type 1 supernova. It's a very smooth, uniform explosion. You can tell this. It basically looks like a big fuzzy. Now, I told you a little bit ago that the Chandra instrument, the ACIS instrument sees color. So you can color this with the softer X-rays, we'll call them the lower energy X-rays in red and the higher energy X-rays in blue. And we get this, but it still is basically just a mixed up jumble of very smooth froth. And that is all that is left of this particular star. Let's see, I want to move to a different supernova remnant, and we're going to play the game a little bit differently. This one's called Cassiopeia A. This is our first light object. And immediately what we discovered was there's a neutron star sitting in the middle of this, but you can see that this one is not so smooth. This is called a core collapse supernova. This is the big, it comes in and it goes out and everything is just a mess. But we can use these colors, these energies, and we know that certain energies are related to certain atoms, whether it's silicon, sulfur, argon, and we can just color the different atoms differently, and we actually create different images. We overlay all those images, that's the image we get. What you're seeing here now has real physical meaning. We can see that the ejecta on this part of the core is iron rich, but there's not a lot of iron here. This is very, very hard X-rays, so we think those are coming from cosmic rays coming in and heating what they call the leading edge or the shock front. So that's sort of the hottest part of the supernova remnant. And this jet here is clearly silicon and sulfur rich. So by this color imaging, we can get an idea of how the constituents of the supernova are arranged after explosion. Now, it turns out that Chandra only sees about 80% of the star. Webb sees the other 20% of the star, the cold part, the dust that's left behind. And so this gives us a very complete picture of what's going on. There's basically a chunk of the star here that never got superheated or isn't superheated now. And then there's dust outside of the supernova remnant that's still cold because the supernova shock wave hasn't arrived there yet. And because we're from Boston, there's a green monster left over in between because we don't know exactly what's going on there. So this is, actually I'll go back one. This is the sharpest image of the Cassia supernova remnant we're ever going to be able to make. And that is because it is moving. And we can see it moving. If you focus on this, about 13 years worth of data I'm going to show you here, but if you focus on the areas with the arrows, and we'll zoom in a second, we see motion. And so we simply can't take a sharper image if it's not going to hold still. But this is telling us about how fast the various filaments are moving and how much material is in each one of them. This is the last supernova I'm going to spend a lot of time on. This is also one of my favorites. I giggled when I saw this the first time. I think I saw this in a Star Trek episode before I actually saw it on the monitor. It just looks like something that you would have. If someone said, draw me a spacey thing that's spinning around and shooting out jets and put it outside the port window of the Star Trek Enterprise, this is pretty much what I would have drawn. But this is an image. This is real. What you're seeing there is a neutron star in the middle, but it's highly magnetized. It's spinning very quickly. It's shooting jets of material up and down. And then this disk is not accreting, but it's actually being driven away. And I'll prove that to you in a moment. But first, I want to show you how it kind of plays with the lower energies, the optical material, which is ionized gas, the infrared dust, and the radio magnetic fields. But the engine of the whole thing is clearly in the middle here, this X-ray source. And so I'm going to put side by side Cassiopeia A and the Crab Nebula. And I want you to I like the Crab Nebula better in this because it's just so very dynamic. And you can actually see, I said it was an excretion disk, it's going away, and now I've proved it with this image. You can also see some of those condensations moving around. There's a period in taking this data where we took one picture every month. And you can see in the individual months, those individual clumps moving. It's eye-opening how dynamic the universe really is, even at these things very, very far away. And that's just a little bit of a community portrait of some of our favorite supernova remnants. I don't think it's all of them, but it might be all the really, really pretty ones, or at least the ones that Laura thought were the prettiest because she put this slide together and I stole it from someone who stole it from her. But, you know, they're not all the same. You would think a supernova remnant is a star blew up, so it's going to look like a blown up star. But they all have very different structures to them. Staying on the subject of these extreme physics, Chandra has really changed our understanding of neutron stars and white dwarfs as well. And my friend Dave Pulley showed me this picture. This is a globular cluster, which should be a bunch of old, boring stars, should be doing nothing, taken with the Einstein experiment back in the 70s. This was a 3-hour image. Einstein was in one of these low Earth orbits, didn't have a lot of time to actually observe, and said, wow, the globular cluster is an X-ray source. That's pretty much all it could tell us, but that's what it told us. There's a German mission called ROSAT that flew in the 90s, and they looked at this cluster for about a day and said, wow, there's a couple of X-ray sources in there. Isn't that interesting? Don't know why. Chandra, we looked for about a week here in this image, and what we see are about 100 X-ray sources, and some of them are these red ones that are relatively cool. Some of them are blue ones that are relatively warm. And really they're giving us insight into both the white dwarfs, which are the red ones, and cataclysmic variables, neutron stars. I think the neutron stars are, well, some of the neutron stars are red and some of the neutron stars are blue, depending on whether or not they're accreting. And there are millisecond pulsars in there. And most globular clusters look a little bit like this, but they're not exactly the same. Some of them have more white dwarfs, some of them have more neutron stars, and that's actually telling us about the dynamics of the individual cluster. So we're actually learning which clusters, that globular clusters themselves have their own differences between them, which is something that at least when I was growing up and looking at pictures of globular clusters in the magazines, they all basically look the same, but it turns out they're not. Turns out each of them has their own ecosystem. All right, and that brings us to suns and the worlds in context. And from my perspective, the universe is made of stars. Okay, if you were paying attention earlier, 4% of the universe is made of stars, but we're going to focus on that because that's the part you can actually look at. And some of the stars start out as these big blue giants and then collapse into black holes. Some of them are a little bit smaller and give rise to the complicated supernovae. Some of them give rise to smaller explosions and white dwarfs. Some of them are cursed to have planets with people around them, and some of them seem to live forever, may or may not end up a white dwarf in the age of the solar system. And the ones at the very bottom here are called brown dwarfs. I don't have time to talk about them, but I could. These regions of star formation are just beautiful. What you're seeing here, this is a strict X-ray image over here. This is X-ray plus infrared. In the strict X-ray image, all those dots are individual young stars. You're seeing clusters of stars here with 300 or 400 or 500 stars in them. You're seeing this very large gas emission that's being heated by some of the more massive stars. This area is supposed to have had somewhere in the neighborhood of 40 supernovae go off on it already. Cygnus OB2 is in the northern hemisphere. It's another very complicated star-forming region. It's a little bit closer. We have a very deep inventory. One of the things I like about this image is that what you can see is the superheated gas here is filling the cavities in dust. So the stars are heating and pushing high energy material into the universe and then pushing this dust out of the way. And in some of the cases, we actually see then that dust collapses and makes another generation of stars. This is a good example of that. This one's beautiful. It's called the Lobster Eye Nebula. And again, we're seeing both the infrared. I believe the infrared here is from UCERT, the ground-based optical. And the purplish stuff here, these are all stars just being formed, and they're happening right at the edges of these dust clouds, and sometimes in between the dust clouds here. So the star formation of one generation is physically driving the next generation. I'm going to focus in on one example, the Orion Nebula, which I hope you all know where it is roughly in the sky, and don't mistake it for drones. So this is actually an X-ray image over here taken with ROSAT, but you can see the belts of Orion pretty clearly. This is a star called Sigma Ori, and then this is the knee of Orion, or the sword of Orion, which is the Orion Nebular Cluster. The image here on the other side was taken with the Einstein satellite, so that one that I showed a couple images ago, very low resolution, but for its day, outstanding in the 80s. That is the best we could do with the ROSAT telescope in the 90s. That image overall, there are about 380 stars we could identify in the Orion Nebula. They're all the older stars or lower mass stars mostly. About 1/10 of 1% of their energy comes out in the X-rays, and it varies a little bit. This is what we knew. That is what Chandra does. And it's night and day. Let me just go back and do that again, because I like to. It's fun. You go from that to that. That image has about 1,000 stars in it. And what we can now start dividing the accreting stars and the non-accreting stars and see which ones were brighter, which was surprising. We got all the way down to the brown dwarfs in the cluster. There's actually a cluster behind this that we identified that hadn't been seen previously. And I'll comment about the variability of these objects in about 2 slides. We then, this name predates anything from this decade or the previous decade, took over the telescope for about 10 days in January of 2003 and stared at Orion nonstop. And the result was this image. And the colors you see here are basically real. The softer X-rays are red, the harder X-rays are blue. There's something like 1,400 sources in this image, and this is basically a complete X-ray study of this star-forming region, the only time we've ever done this for something this massive. And then you could compare this to the best available ground-based telescopes. And if you pick any one star, you're going to immediately find the infrared companion for that star. Except every now and then, we detected a star that wasn't detected in the infrared because it's too faint and maybe it flared in the X-ray. I want to zoom in briefly on this area called the Becklin-Neugebauer object, or the Kleinman-Low Nebula, just to really drive home how much Chandra matches an 8-meter. Now, I told you the Chandra collecting area is about like this. It's a 14-inch telescope, effectively, but it's seeing as deep as the 8-meter telescope of the greatest technology at the time, the VLT, and really matching it source for source, resolution for resolution. This is where we are today. That's the James Webb image. Again, there's not a lot there that James Webb can see that we can't. We're just following up the same sources. We have gone back to this field periodically for different reasons. So we've measured the changes over these stars, both in the short term and the long term. And I've mentioned that these stars vary. This is that 10-day image. I want anyone and everyone to pick a star, just stare at it. It's a little bit like Christmas. Everything flickers, and this is your universe. You can imagine the sun doing this, and it would not be particularly a good day. And we'll get back to that theme in a few minutes. But these stars are very, very bright in X-ray. They're very, very active, and this matters. I want to make sure the sound is on as I go to my next slide. So this is the other thing you can do with Chandra. Instead of just imaging, we can also put those gratings in the way. You remember the gratings? I mentioned them about 45 minutes ago. Well, you can use them here, and you can get grating images for all those stars. And what that means is now I'm not just going to say neon, I'm not just going to say oxygen, I'm going to say silicon with 12 of its electrons removed, sulfur with 13 electrons removed, if it even has 13, magnesium with 11 electrons removed, iron with 22 electrons removed. These things are really, really hot and can only occur in certain configurations of density. So we've done this measurement with this particular image for 36 different stars of all different spectral types. And really we can measure the altitude of the corona over the photosphere, the temperature and the density, and how these things vary as they go up in altitude over the surface of the star. This is a unique capability. And I'm going to hold this here while Casey takes that picture. Oh, what's this? I hope that didn't violate any copyrights. So I believe Larry mentioned I was a flight director. And people don't particularly know what that means. It sounds important, but it doesn't really, been in a couple movies, I guess. But what it means is that that sound is the sound that wakes me up at night. That is the sound of something going wrong. Fortunately, I don't get that sound terribly often, but I did a couple of years ago. And I think the only way you can explain what the role of a flight director is to kind of walk through it. So this is what happened on a particular Monday, and this always happens this way. It's either I'm just waking up, just going into the shower, or just going to bed. That's the only time this ever happens, as far as I've figured out. And all you get is a message that says, in this case, that a stored command sequence has finished running that was not supposed to run. And call this number now, and I'll tell you what's somewhere will tell you what's going on. This page will go to about 50 people or so in Massachusetts, New Hampshire, and Alabama. And all those people will stop what they're doing at that moment, including if they are attending a sporting event, which has happened more than once, and go to a quiet place to dial a phone and find out what's going on. Being a flight director means that you'll eventually have to be in charge. So the first thing you do is you look at your cheat sheet and try to remind yourself what you're supposed to be thinking about. This is actually my partner's who keeps it in his wallet, and that is still the original copy that he got in 2002. A minute after that, you dial in, and the flight director is responsible for everything and allowed to do nothing. It is one of those jobs. So you have ultimate responsibility and absolutely no capability, which is a good descriptor for a lot of things. So what happens here is you'll be on a phone call, and there will be the people who are actually physically commanding the spacecraft, and they will be going through a series of procedures on what to do when something goes wrong, and following a little fault tree. There will be a group of people that are or particular person here who's the ground operator. His job is to make sure that the spacecraft doesn't lose communication with DSN, the Deep Space Network, and they don't lose communication with us. Often we only have a 1 hour communication window. So kind of the first thing we do is say, can we stay on the phone a little bit longer to make sure we know what's going on? Sometimes the answer is no, but we ask. The spacecraft instrument teams for the ACES and the HRC will be there. And each of the subsystem engineers will be there. Mission planners will be there to find out what they have to do next. NASA is on the phone, and our lead systems engineer. My job is to listen to everybody and to sort of make sure we're following through and doing things right. Because a lot of people are thinking about a lot of individual detailed things. Flight director has to think about everything. So, what is that? Master of nothing. So in this process for about the next hour, because that's the typical duration of the comm, the first thing we determined the spacecraft was safe. It was getting solar energy onto its arrays, no problem. There's a slight error in the pointing that turned out to be about 2 arc minutes in this case, which is something that had happened before. But the spacecraft probably took a long maneuver. There's a little error in the beginning, and then maybe a hiccup with the gyro in the middle, and it missed, in this case, by 2 arc minutes. It was actually quite frustrating. It could have kept going, but we had put constraints on it that said, no, call home when this happens. So the recommendation was to proceed with the recovery, but it's midnight, and we don't want people doing that when they're too tired. So we're going to go and deal with it in the morning. So about 12:15, you send out an email to the director and to our contact program manager at Marshall, and basically say, this is what we saw. This is what we think the problem is. This is what we've done already. And this is what we're going to do tomorrow. By the way, tomorrow the Deep Space Network is going to be off for most of the day. They have work to do for maintenance. So we're going to have to get up very early and then come back very late. which meant that Tuesday was a long day. We got up on the spacecraft at about 6 o'clock in the morning, a little bit before that, and took a picture with the guide camera, identified the part of space we were in. It then locked onto guide stars, so it was no longer basically holding still and waiting. It was now locked onto a star pattern. It didn't recognize it, but it said, okay, I'll stay staring at those stars until I tell you otherwise, or until it's told otherwise. By 8 o'clock, we were done with that, so about 2 hours. And then sent a message saying, okay, we're good, we're tracking, or we're holding, we're just about ready to go. And then we have a 9 o'clock meeting, inform the entire community of our status, take questions, and then spend the day getting the spacecraft ready for going back to science, because the schedule's been interrupted. Did we miss anything important? What do we have to get done? What shuffling has to be done to the schedule? That took, at that point, most of the day to develop and then release to engineers who got a chance to look at everything, make sure nobody makes a mistake. That gets approved around 7 o'clock and gets sent to my desk around 8 o'clock for, okay, has everyone looked at this and everyone's okay with it, then we're going to do it. Then about 10 o'clock, DSN says, okay, you can have the spacecraft back. We upload the coordinates of those stars we've been looking at, because now we know where we're pointing. And everything syncs up and the spacecraft goes on its merry way, and we're very happy. And this is the group of people that gets that done. This is our operations control center. I'm the bald guy in the back here. The instrument teams are in the front. The engineers are in the middle. And the command controller is over here. The lead systems engineer is supposed to be over there. I'm not sure if he's in that picture or not. But this is our control facility in Burlington, Massachusetts, about 8-9 miles away from Harvard. We started at MIT, and a whole bunch of biotechs started to move in around us, and the rent just went up ridiculously, so we had to move. Okay, so Wednesday comes, and we start getting back to normal, write an anomaly report. It's sort of a one-page description of what I just told you, and the fact that we lost about 24 hours worth of data, which we really don't like, and some corrective action. And this one was a very nice one because it taught us a lot about how the spacecraft was going to operate going forward. And we kind of changed our air circle and made it a little bit bigger. Thursday, there's a flight directors board meeting where all the chief engineer from Marshall and the chief engineer locally in Massachusetts get a chance to communicate, and any changes we want to put forward in operations are going to be discussed. So the fact that we changed some of our settings is discussed and approved by a large group at this point. There are 3 flight directors at this point. Tom and I have been doing this for almost 10 years, and we brought on Jan recently because we were getting sick of only staring at each other. It's actually much easier with 3 people because we don't have to totally coordinate the fact that our vacations are back to back. So what a flight director does is basically manage and process control. There's a weekly meeting, which are any processes that have changed, but it's really being part of the mission planning working group and the thermal working group and the software working group. All the products, everything that ever happens in the mission has to come through the flight director at the end of the day. So you have to be able to have confidence that you know what the spacecraft is doing, why it's doing it, and that it's doing it correctly. So the simplest change, like saying that an appropriate voltage for the spacecraft used to be 28 and now it's 27.5, and we're going to tell someone to look at a console screen and look for 27.5 now instead of 28, eventually has to be proven to the flight director to be safe, and then the flight director says, okay, now it's all right for that engineer to accept that particular value. And every week we write a memo to NASA headquarters saying what happened in the previous week, for good or ill. But that's not really Chandra's job. The job that we were given in the Chandra X-ray Center, which is my immediate employer, is to maximize the science return from Chandra. And that's what we think we do. We try to stay on target doing science as much as possible. And I want to make this talk about science as much as possible, which gets us back to our decadal theme, worlds and suns in context, exploring habitable planets. And this is my favorite image. I talked to Harvey Tannenbaum at a meeting about 6 weeks ago. I showed him this image, and what this image is this is every pretty much planet in the solar system, one comet, one not planet, but we love you anyway, and the moon. Every single one of these has been detected by Chandra. And so I talked to Harvey, who wrote that proposal in 1976 I showed you, and I said, Harvey, did you ever in your wildest dreams imagine that 50 years from writing that proposal, I would be showing you something like this? And he just shook his head. This is nothing we expected. And what's amazing about this image is it is all kinds of physics. It is charge exchange. It is fluorescence. The rings are scattered, or the rings emit photons because they're forward scattering bright lightning. These are aurorae. This is fluorescence on the dark side of the moon. So this isn't sun. This is real signal that's coming from not fluorescence of the sun, but actually intrinsic. This is actually, I have to remember what this is. This is actually X-rays being emitted in the high up altitude atmosphere between the Earth and the moon. That's what that is. And then I want you to look at Mars here. So this is Mars. These are X-rays coming off the face of Mars. And then there's this stuff. These little, I told you, I think, that we basically don't have noise on Chandra. So this is signal. What this is signal of is high energy protons being fired off from the sun, hitting a neutral particle high up above Mars, and then grabbing an electron from that high energy, that cold particle, and driving it down to the high energy particle, because high energy particles need electrons, and emitting an X-ray. What's that cold neutral? That cold neutral used to be the atmosphere of Mars. This image is showing the Martian atmosphere boiling away right now. Which brings us to habitability. So this is a figure put together about 8 years ago now, 7, of all the things that feed into, is a planet habitable? Obviously, the orbit, the mass, but the interesting thing here is all these purple things come from X-ray science. Does the atmosphere escape? How bright? Well, that depends on the activity of the star and the luminosity evolution of the star, some of which depends on the age of the star, and which kind of depends on the rotation of the star, but these kind of all these things really are only directly observable through X-rays. And I'm going to go the other way on this. This is a map of most of the known exoplanets and 4 of the planets. This is the distance we are from the host star, and this is the mass of the planet. What I've added here to the normal plot is Jupiter, Saturn, Venus, and Earth. And what you notice is that we aren't part of the plot, right? We wouldn't be detectable. Our solar system is not the kind of solar systems we've been looking at with all of our wonderful 5,000 odd detections. We focus on systems, and I'm going to go the other way here, that are close. And the reason for that is because you can study them. Turns out if there's a habitable planet around a G star, it takes about a year for that system to transit, which means it takes a long time to build up signal. So we tend to look for things about low mass stars. The problem with low mass stars is while they are much, much fainter optically, which means you get a habitable planet to be much, much closer, they're also about the same X-ray activity. That doesn't change with mass. So the net result is the X-ray irradiance that an exoplanet experiences around an M star is much, much greater than you experience here on Earth. So we'll just snap through these and talk about the obvious. X-rays from a star are going to affect the exoplanet. We actually see that in the optical. We see in the optical that hot Jupiters are bigger than they're supposed to be. And that's because of X-ray and UV light being added to the optical light in terms of the heating. It can also be a good thing. X-rays lead to photochemistry, which can be prebiotic chemistry, which is what we want to do to create life, so that's good. It can be a bad thing because you can start to irradiate these atmospheres and they can actually escape into space, as I showed you a few minutes ago. What that means is for some of our first exoplanet systems we looked at, I keep doing that, is that they've actually lost almost half, or in this case, 3/4 of their original mass, just burned away to space because of the X-ray flux of the host star. The other thing that was kind of interesting is that exoplanets can affect their host star. I mean, you got this giant star and this little exoplanet. You wouldn't think that the dog could wag the master, but it's absolutely what happens. And the reason is it's just like the moon, right? So the moon rotates the Earth slower than the Earth's orbit. So it raises a tide that kind of drags the Earth backward. And we've all read that back in the day of the dinosaurs, there were 400 days in a year. And now there's about 365. And that slowing is because the moon under-rotates the Earth and everything slows down. In the case of a hot Jupiter, it takes about 8 days, 3 days, 4 days, something like that, for the hot Jupiter to orbit a star. But a star like the sun rotates in about 30 days. So in that case, a tide will drag the star forward and make the star spin up. And faster things rotate, the more active they can be. And this is a better figure for all that. In addition, you have these magnetic fields. You can imagine the sun's magnetic field and Jupiter's magnetic field. And if you put these things close, they're going to spark. So you have all this energy moving back and forth. And I just want to talk about one exoplanet system for the rest of the time. I'm talking about exoplanets. That's HD 189733. This is one of the first ones discovered. And in this image, this is the A star. It has an exoplanet with an 8-day period. That's the B star. It doesn't have an exoplanet. That just happens to be a background AGN. The wonderful thing about Chandra is these are 3 individual point sources with Chandra. You need the kind of resolution we have. This is just a representation of the system. This is the sun during a solar eclipse. And this is a corona of the same strength as in 189733. I put a planet 8 stellar radii away, and you can see it lives its life in the thick part of the corona. We have seen flares from this star that are about 4 our star, 4 times the radius of the star. I have a wonderful PR department, and they put together this video that basically describes what that planet experienced the day we saw the very large flare. And in NASA parlance, that is a bad day for the planet. And that's just about 3 days of observing this particular system, and we saw that flare. So the other thing that Larry described, and this is getting towards my finish, is that I've looked at the transits of exoplanets in X-ray. So this is a transit of exoplanets in the optical. You guys are familiar with this. The exoplanet goes across, and the star gets a little bit fainter. In the X-ray, things are a little bit more complicated because the star has this very large, thin, extended atmosphere, and the planet has a large, thin, extended atmosphere. So you have a very complicated signal here. It's not really a top hat. You have a maximum loss of signals about there, then it gets brighter, then it gets fainter again. So this is what you see for 189733 in the optical. So that's just a pebble going across, and that pebble is 2% of the area of the star, and therefore you get a 2% drop in the flux from the star. This is what we see in the X-ray, and for those of you in the back of the room, it's very easy to tell that there's even deeper transit in the X-ray than in the optical. We fit that with this curve, and that gives you this extra atmosphere here that's about 75% bigger than the optical star. And with that, you can go and do a little bit of arithmetic and create an atmosphere for that star and a temperature and a density for that upper part of the atmosphere. So this is what we were able to do in this particular case. These cases this is difficult. The X-rays are faint, and you have to look for a lot of transits and add up the data to do this. I'm going to skip over that because we talked about Jupiter already. And what's next? Lots to do, lots to do. Chandra now has a legacy program, which is what do we have to get done because only Chandra can do it. This includes studying that baryon cycle that I referred to previously, and also looking at clusters of galaxies and the cooling structure of these things. This requires a tremendous resolution and a lot of observing time. But what you can do is you can basically understand the full energy budget, not for one star, not for one galaxy, but these entire clusters of galaxies, which is really the heartbeat of the entire universe. And we now have a new playmate. So in this image of the Cartwheel Galaxy, the purple is all X-ray. That's star formation. The Webb is seeing the dust and the stars. This is one of my favorite star forming regions here in Cygnus, and you see some diffuse gas and some pointed stars. This is another one of those galactic clusters, except now this is much further away, and that's going to be important in a moment, and then where the matter is. Here is the Chandra image I showed you a little bit ago with the Webb image. And now you can really see the interplay of the dust and the magnetic fields that Chandra shows. I'm going to end the sciencey part of the talk with this. This is an image now from I think about a year ago. So James Webb has looked at some fields for a very, very long time, taking deep, deep, deep exposures, and they do it in a whole bunch of filters. And if you see a colorful galaxy like this one, it's probably relatively close. But if it's only red, if it's one of these little red dots, then it has to be very far away because the universe is opaque at certain blue energies. And then as you redshift things, those blue energies, of course, redshift out and become redder and redder. So if you can only see something in the extreme red, it's got to be very far away. So this thing is at about, I'm forgetting at the moment, and my notes aren't terribly easy for me to read at the moment, but it's about Z of 12. So this is about when the universe is 300,000 years old. 300 million years old, when you can see this guy. All right, so the universe is approximately 1/12 its current age, a few hundred million years. That's geologic time on Earth. And it's an X-ray source. So this says that galaxies, groups of stars, got together right at the beginning of time, 300 million years after the Big Bang. This says, and they had supermassive black holes in the middle of them. This says that all those early galaxies already had supermassive black holes right in the beginning. And when Chandra was formed, the question was, well, you can't make supermassive black holes at the beginning. They have to kind of be created. It must be a generational thing. We don't expect to see any supermassive black holes early on. Now, we think that, well, actually, these galaxies are created because that early structure, remember that dark matter I talked about and the regular matter? They were closely coupled at the beginning of time. And so things sunk in. And now we think, well, of course, black holes must be at the center of all the original galaxies. And now we expect to see them everywhere. Moving on, Chandra. Well, there's nothing on Chandra that means it's going to die anytime soon, but it may or may not live forever. But we're still doing science with 14-inch telescope. So AXIS has been approved as a phase A study, one of 2 possible probe missions moving forward. This now has effective area equivalent to about a 27-inch telescope. So it's about 5 times the effective area of Chandra and a resolution that is on par with Chandra. So we hope this launches middle next decade, early next decade, and this is the next step in terms of seeing deeper into the X-ray universe. All right, I was told you should always finish a talk on a high note. And I want to take that literally. I want to talk about something that we've done with the Chandra program, working with the Perkins School for the Blind, to bring what I have just shown you to the blind. These are gorgeous images, I think. I think you'll agree. But it shouldn't be limited. Science is not limited to sighted people. So we have a recent movie out how this is done called Listen to the Universe. It should still be on the NASA website. This is what we do. We take that image of Cassiopeia A and we assign, think of the violin stringed instruments. And I hope the sound is on now. And we assign a different stringed instrument to each of the wavelengths of light. And so this is how this works. Just follow that little white dot. That. Is the Concerto of Cassiopeia A. But the other supernova I showed you sounds completely different because it's a different supernova. It's a different type of supernova. The different types actually have different sounds. You can identify them by their sounds. And finally, there's this one, which is in fact a sound wave. This is the cooling flow from the Centaurus A cluster. And it was described as a sound wave with a frequency of 88 octaves below middle C. We can't hear that, but we can actually compress it and bring it up. All right, so why do we do this? Sometimes it's simple. It's just wondrous. Sometimes it's physics. I'm more on the wondrous side, but in its 25 years, Chandra has enabled transformative science from the very close to the very far, mass functions, dual AGN, clusters of hundreds and thousands of galaxies. And as predicted, every area of astronomy has been profoundly influenced. And the best is yet to come. And to prove that, this is the 25 images released for the 25th anniversary of Chandra. I literally only spoke to one of those in this whole talk. There's a lot more out there. Thank you.
Thank you. We have time for some questions. Blue microphone.
All right. Hello. Can you hear me? Okay.
Excellent.
James Coe. I'm a member of the club. And my question, you mentioned the difficulty of imaging X-rays. And I'm interested in some of the methodologies. You mentioned these long grazing angle focusing. But I also am aware that there's such technologies as coated aperture,
Yes.
X-ray imaging, and Lau lenses, which make use of crystals and diffractive methods. And can you comment on the efficiency of these methods and maybe in future missions?
They do different things. The coated aperture we use in our group to image the sun. They allow you to focus on a narrow wavelength of light and you need a lot of light, but it allows you to use the normal incidence optics, and then you put a coating on that causes an interference, which then sort of traps the one wavelength you want to look at. Some of these other technologies like Fresnel lenses are similar in that they can be made very big, but they don't focus very well. So they'll have a very blurry image. So lobster eye optics and Fresnel lens type optics are good for telling you there's an X-ray over there. Probably about there. Okay, it's not quite as accurate as pointing a finger, but it is as accurate as pointing a hand. So it's good for all sky surveys, all sky monitoring, looking for a follow-up to one of these gravity wave events. If you hear a chirp and you see a flash on one of these all sky monitors, then you know where to point something with a little bit more focusing ability. So they work hand in glove.
Red microphone.
I'm Bob Hershey. I'm a member. What are you finding about exoplanets?
So in our most recent paper, we're finding that the exoplanets where we are looking for life right now are difficult. James Webb has done follow-up on a whole bunch of really promising candidates, and a lot of them turn out to be bare rocks. And one of the reasons we suspect they turn out to be bare rocks is this long-lived irradiation from very active stars. But in the thing we're working on right now, we were able to sort of find corner cases where we demonstrated that if you have a thick atmosphere like Venus, and you have a lot of oceans of material, maybe 10, maybe 11, that in that case, yeah, you'll burn off material, but you'll also be able to replace it, and it becomes a race. Do you have enough volatile material to outlast the life of the active star, burning it away? But we think there's a case. We would suspect that in about 90% of cases, no. But about 10% of the cases, you should actually find a remnant atmosphere. And the good news is there are a lot of M stars out there. So there's a lot of places to go and look.
Blue microphone.
Claude, I'm a member. You showed an enormous variety in supernova remnants. They all seem different somehow. I don't know how well that's understood, but dark energy observations assume that supernova type 1a were all basically the same.
Yeah.
So does this difference in them affect that conclusion?
So I was showing you both type 1s and type 2s. And the type 1 is the one from a couple ago, that very smooth exterior. That's a type 1 where we absolutely know the mass of the progenitor and how everything happened, and it was a very uniform explosion. So that just is to say that we can actually tell which is which, but when we're estimating the mass or the value of lambda, we don't care. We absolutely don't. The supernova could change throughout time. We'd still get the same answer. The fact that the supernova experiment matches our data indicates that the supernova standard candle works. So it appears, based on combining our observations with theirs, that this is okay.
Thank you. May I follow up that you showed different silicon and iron in different regions of the supernova remnant. Is there any understanding of how that separation between different elements comes in the supernova explosion?
So the short answer is yes, but I don't know it.
Thank you.
All right, red microphone.
Thank you for the presentation. Ravi Deepak, member. Very exciting career that you shared with us, and I'd like to see the next evolution with Axis. But I had a question on the exoplanets, specifically about like maybe correlating between Kepler's exoplanet discoveries and your own. What have you guys found as far as?
I don't discover exoplanets.
Sure.
So what I showed there was a sum total of TESS, Kepler, and a lot of ground-based projects that look both for transits and for the radio velocity experiments. What we try to do is look up some of the more interesting systems and understand what the X-rays are doing in that particular system. So we've studied about a dozen or 2 dozen, and the net is most of the ones that are in these, especially the super Earths that are in these studies that have been found around low mass stars, they tend to have X-ray radiation experiences that are much, much higher than the Earth. So this is feeding into this problem of we're looking effectively under the street lamp for the habitable systems, but the street lamp is also so bright that it might be burning away the very atmospheres we're looking for.
Yeah, there are, the coverage for exoplanet detection is skewed because of the methods and their limitations. We are going to have a talk, let's see, on March 21st by David Bennett, and he's going to be talking about using microlensing to detect exoplanets, and it has a different profile of the sort of planets it can see, fill in some of the gaps in the mass and distance distribution of what we've been seeing. So, all right, we have, I think, the red microphone, blue microphone.
Hello, this is on? Yeah.
Go ahead.
Okay. Victor Vahidi-Moti, I'm a member. When I was listening to your sources of different sources of X-ray, I was imagining that it might be theoretically possible that cosmic microwave background will be shifted to X-ray through reverse Compton scattering at the active galactic nuclei. Have you ever observed that phenomenon?
So there is observed X-ray Compton scattering from the background, not directly from the microwave background, but yes, that effect does occur.
Any other questions? I think there are no other questions. Somebody? Casey.
Oh dear.
This on?
Blue microphone,
this is
blue microphone.
My host, so.
The blue microphone, it's on.
Yes. So tell us a little bit more
Who
about
are you?
I'm Carrie Liss. I'm a member. I'm also
Thank
the
you.
fellow who helped get Scott come down here to talk. We're fellow astronomers. We work together a lot. Scott, how often have you, in the course of 25 years of Chandra, how many upsets have there been? And if you will, the one you just talked about, was that a mild one?
That's a very minor one.
Was there anything that actually scared you?
Yeah, so we've had 7 safe modes total in 25 years. Other mild upsets like this are just safe-ish modes. They don't actually take us to safe mode. 6 of those safe modes are directly attributable to programming error by the team, by the plan. We didn't leave enough time for instruments to settle before moving was one of them. Second one, we did things in the opposite order that we were supposed to because we had never realized that a particular step was order controlled. One in 25 years stumped us. And I loved it because it was during what we call a NASA quarterly, where our NASA bosses were literally all up in Cambridge, and 8 of us suddenly stand up and leave the room. Never good. And then when we come back to tell our boss what's going on, we're like, we don't really know. 2 days later, the whole thing worked itself out because what had happened was that the information about, we write our data onto a solid state recorder and it writes, and then there's a read head that plays back to us. And we simply had lost the data of the event. We had no idea what had happened. And about 3 days later, one of our ground controllers pointed out that the read heads and the write heads are actual physical things on this recorder, and they can't actually touch each other. So we'd actually had to move back one of the write head and then move back the read head, and then we could play back the 78 seconds we were missing. And all of a sudden we knew that literally all that happened was a gyro had done one of those glitches, and we couldn't find it, and it had us somewhat freaked out for 48 hours, although Hubble had a freak out at the exact same time, and that one was already in the papers, so our jobs were to keep Chandra out of the papers. We succeeded in that, and everything worked out. It took us about a week for that particular event, and that's one of these ones where we were working till 2 or 3 in the morning a couple of times. The good news was it was October. It was the first or second week of October, which meant that baseball playoffs were going on into the wee hours of the morning, and I could actually listen to baseball games driving home. So very, very rarely has anything actually scared me.
We're going to take a question from the web with the blue microphone, or no, just from the web there. And then we'll do the blue, but first the web.
Question from the web comes from Michael Haken in Silver Spring, who is a member. Can you comment on the theoretical explanation for the striking north-south pole asymmetry in the X-ray structure of the Crab Nebula pulsar?
I cannot, except that part of it is look angle. So the southern pole is beaming at us, and when we're looking at that northern pole, and I'm doing this exactly the wrong way, so the southern pole is coming right at us. The northern pole is going away from us through the disk. So we see that through the disk. And so a lot of that is an impression given because we're seeing all the diffuse material. And we've actually generated some 3D models in part of our outreach group. And those 3D models do indicate that if you can move the image around, it's symmetric. So a lot of that is a little bit deceptive on the part of the look angle.
Thank you.
Blue microphone.
Brett Magrum, I'm a member. So what's next? Is there plans for a bigger, more powerful X-ray telescope? And when would that launch?
Okay, so there's a couple of things. I showed you a couple slides ago the proposed next mission that is currently in a Phase A study. That's not quite as bold of a concept as Chandra. It's basically a bigger Chandra that does a lot of the things we can do a little bit more deeply. There is a design that was proposed in 2020 that we're working on a revision of called LYNX, which is for the great sensitivity that the Lynx cat has. That would be about a factor of, I think it's about 50 bigger than Chandra. Technology we think we understand how to do, and also has more advanced detectors. The Axis instrument has detectors very similar to Chandra, but the ones that would fly on LYNX include a energy-sensitive detector that's called a microcalorimeter that measures the amount of warming that each X-ray deposits into the detector. So it is a true imaging spectrometer. It has as much energy sensitivity as a grating. So that's really what we're looking to build, is something with that fantastic energy resolution and fantastic spatial resolution with this very large collecting area. And we have designs for how to do that. The only limitation is the federal budget, which is, of course, a very minor issue around here.
Okay, I guess I have, are those photon counting?
Yes.
Pixels?
Yes.
And these would be photon counting?
Yes. Everything you see here was created by a photon counting device.
Okay, we have a question
more.
somewhere. What color? From the web. One more from our online audience.
From Shrevan from Melbourne, Australia, who is not a member. Which X-ray sources are your favorite? And which do you think should be studied in the future telescopes that are planned?
Okay, so that's sort of two different things.
Yeah, I was going to say, and are those the same things?
You know, I think fundamental physics will come from the galaxy clusters. We can improve our understanding and refine the values of these fundamental constants just by seeing more of them at different distances and seeing how the universal evolution, how the universe has evolved in time. That tells us exactly the future of the universe. In terms of what is my favorite, that has to be HD 189733. That's the gift that keeps on giving. Not only have we measured directly the atmosphere of this exoplanet in X-rays at incredibly high altitudes, we know with future instruments we'll be able to measure the different elements as a function of altitude. So there's more to be seen there. And then because it has this, because the exoplanet is very, very close, we know that this star is actually older than it appears. So if you use the normal techniques for figuring out the age of the star, it looks like a young star. But it had that M counterpart, and that M counterpart is a very old star. So we know the system is actually much older than it appears, and it's because of this spin-up process, which we've now found in half a dozen systems. So one of the tricks here is that if you do have one of these hot Jupiters and you do think it's a young star, You could be wrong. It could be a young star that's experiencing a second youth because it has a pet to walk a lot. So to me, that's just been it's been an interesting system because of a whole list of reasons. Me and my postdoc, before she was my postdoc, argued over what was the best observation to do here. We both submitted proposals. They both got the exact same grade from the proposal evaluation committee, and that came with the orders of Chandra should only do one of these two observations.
No.
At which point my boss calls me, the director of the observatory, Harvey Tannenbaum. He says, this is what has happened. He says, what do you think my answer is going to be? Obviously, I'm going to let the other group do the observation, not my own person. I said, that's fine. I just hired her. So it all worked out.
Well, Scott, I think we're done with the Q&A, so thank you so much for giving this talk. Before you go, we have a few small gifts for you, which are in the back, but so everybody knows what they are. We have a rosette, which is emblazoned on its side with 3 bars, symbolic of the unit for induction, which was studied by Joseph Henry, our founder. I signed a framed copy of the announcement of your talk, signed by all the members of the General Committee on behalf of the membership, and a copy of Volume 1 of the Bulletin of the Philosophical Society of Washington. And in there you will find the founders' names, why they founded the organization, the purposes of the organization, and a nice discussion of what kind of conversation should take place in a society devoted to scientific discourse, which still stands as a good guide for today.
Indeed. Well, thank you very much.
Thank you.
And thank you all for having me.
So before you all go, a few quick remarks about the upcoming lectures and some closing notes. The next lecture, I'm sure that member Frederica DeRema will be very happy to know, is going to be by not just Michael Folkowski, but also Dr. Seaborn, who said just today that he would be able to join Michael. So Michael Seaborn and Michael Folkowski will both be talking about remote sensing of wildfires, which I think is a particularly timely topic, and I hope you'll all come and hear them speak. I should mention, well, the rest of the spring schedule is finally in place, believe it or not. I am not going to go through all of these. You can look through them yourself. Just to say that after Michael and Michael, Robert Smith, who is an historian of Hubble and the JWST, will be coming to talk a little bit about the history of the JWST. It is not in place of the Minute Conference I've been talking about ad nauseum and forever. It is a standalone. The conference will be later because there are too many date conflicts. So hopefully either in the fall or early next year, we will have our mini conference. As I mentioned, another highlight would be David Bennett, and his going to be talking about microlensing to detect exoplanets. And there you have it. Please check the website. I will say one clarification is down here. We're either going to have the CEO and founder of Planet, which is the Earth observation company that does small sats, or we're going to have somebody from Commonwealth Fusion Systems. And we are going to have 3 talks on fusion. We already had one from UCSD's Fusion Engineering Institute. And Commonwealth Fusion Systems is out of MIT, and they are doing tokamak approach, but they have very high Tesla magnets, much higher than has been available until recently, that were developed at MIT. And then I'm hoping we'll have, I can't think of his first name, Scott Hugh maybe, from DOE. He's in charge of DOE's fusion funding. And hopefully the current administration will allow him to come and speak, but we don't know. If not, we'll find another way to get somebody from the government to talk about the way they're funding fusion research. And with that, let's thank our crew. Thank you for running cameras and all of that. With that, I will accept a motion to adjourn the 2508th meeting. Second, all members in favor. The meeting is adjourned.